start. Let me just share my screen. Just give me 1 second. Presentation. Right. Okay, and let me share. Right. So that was sort of a last-minute change. Originally, the plan was that we wanted to talk about template Haskell today, but I think generic programming is basically at least as important, and it's also very nice, and it's also similar. So the plan now is that we do generic programming now, and then I'm not sure whether we have announced that already, that next week we will take a break. So next week there won't be lectures, and we'll continue on the following Monday then. Because next week, my department, so including Karina and Robertino, we have our annual company or department meetup. So we'll continue then Monday in a week's time. But anyway, so the idea now is that we do 2 lectures on meta programming. And one approach is called generic programming, and the other one is called template Haskell. And they are both useful in their own rights. So when I talked about optics, for example, I mentioned that you don't have to write these lenses by hand if you have a record type or something. Instead, you can use template Haskell to automatically derive it for you. And similar, as we will see today, for example, we talked about binary serialization, this binary class. And again, there you don't have to define that by hand. You can use generic programming, generics to automatically derive that for you. It's 2 completely different mechanisms, but they can be used for similar things, like automatically deriving type classes. Okay, so the goal is basically first today, and maybe, I shortened this lecture a bit. There was a 3rd part, but that wouldn't have made sense to us because we didn't talk at all, about type level programming, which we would need for this 3rd part. So anyway, it's only 2 parts. So the first is to introduce the idea, and the second is to show how it's actually implemented in GHC. If one would immediately start with that, that's a bit overwhelming because it looks quite complicated, but the idea itself is actually very pretty and simple. Okay, and right, so from day 1 when we learned Haskell, we started to define our own data types. And that's one of the really nice features of Haskell, that it's extremely lightweight to introduce a data type. For example, I did a lot of C# 10 years ago or so, and then normally you need, I think you don't really need to, but it's good practice to basically have 1 file per class or interface. So you need a new file for every type, if you want to call it type in object-oriented language. So it's quite involved. Even if it's a simple class, it's still a lot of boilerplate. Whereas in Haskell, to define a new data type, in principle, is 1 line or 2 lines. And it's very nice and useful. Introducing new types creates a new type for the compiler. So we can, for example, also using new types, we can distinguish between similar things. So that the compiler checks for us whether we use the right types at the right points. So we have added safety. We can use these names or these new types for domain-specific stuff. So for example, when we write something about blockchains, then we can call our types block or chain or transaction, something like that. And thus basically make the program more readable and not just rely on documentation, but bake it into the program itself. So that's all very wonderful. But they are also sort of problematic, because if you use types, if you just make up ad hoc types, then of course if you don't write it yourself, there's no library working with it. So, I mean, for example, in the beginning, we defined our own list type with just constructors nil and cons. And that's like basically this same as the built-in lists. I mean, under the hood, it's exactly the same, except for this syntactic sugar that built-in lists provide. But of course, you don't have, I mean, for built-in lists, there are all these libraries, all the prelude functions that you can work with them. And for your new type, of course, all of that doesn't exist. So if you need something like that, you have to write it yourself. For example, you can't even compare them for equality or serialize them, deserialize them, traverse them, and so on. So in principle, you would need to write all these instances that already exist for lists yourself. Luckily, it's not that bad because we have this deriving keyword. So these examples here, like I mean, this example, like equality, or all that we can just derive. And that's part of the Haskell standard. So, I mean, this is a bit weird these days because basically the only serious Haskell compiler is GHC. But back in the days, there were some others as well. So, and according to the language standard, every Haskell compiler that supported Haskell 2010, for example, needed to be able to derive these 6 classes: equord, enum, bounded, read, and show. And of course, we have seen that GHC has extensions that allow us to also derive these things: functor, foldable, traversable, typable. I think we only talked about these 3. So we haven't talked about typable, we haven't talked about data, and today we are going to talk about generic. But even with these extensions, I mean, that was 6 and now it's more, and actually there's even more. So when we talk about template Haskell, there's at least one more that you can derive automatically using GHC. But nevertheless, it's still a small number of classes. And for example, binary, that we know from binary serialization, the binary class is not in this list. So neither is it built in, nor does GHC has an extension to derive it. So that's a problem, right? Because I mean, something like binary is not that useful if you always have to do this by hand. And especially in a case like binary, it's also quite tedious because it's more or less clear how to do this. I mean, for every given type that you define, it's more or less obvious how you would serialize it and deserialize it. So the idea of generic programming or generics is that to make this concrete. So if you basically know how I mean, whatever that means, for each reasonable data type to implement it, to actually write a program that actually does this. And so as I already mentioned, there are other options. So template Haskell we will talk about in the next lecture. Then there are also external preprocessors. So you can basically, I mean, GHC has, I mean, there's a pragma that you can use that tells GHC to basically use an external preprocessor. So GHC is sort of extendable and pluggable. And so you can do something like that. For example, Plutus, I mean, the smart contract language Cardano that we'll talk about in the second half of this course, uses that. Yes, so they use a preprocessor, to actually compile Haskell to Plutus core. Or at least a plugin. I'm not sure it's a preprocessor, but anyway, it's a plugin to GHC. So we'll talk about the generic support today. And there are also other libraries that do similar things. This is, I mean, the topic today is called data type generic programming. So we'll first look at the idea, and then we'll talk about this, about GHC generic support and how you can actually use it in practice to, for example, automatically get instances for binary. Okay, yeah, and actually we look at that first. Let me just see what the example is. Yeah, binary. Okay, let me just switch to code then. Just give me a second. Okay. Right. Let me just, as a dependency, this binary. Yeah, yeah, of course. Sorry. Just as a reminder, let me also binary package. Right. Okay. I mean, we did that by hand for some. We see there's a bunch of built provided instances, but of course these provided instances don't apply to custom codes that we just define. Just want okay, and this is how you can actually try it out. Right. So just as an example, so for example, we could let me just open a REPL and import data binary. Now I can, for example, encode, I don't know, a list of pairs of strings and bool. That should already be covered. Okay. And if I give that a name, then I can also decode BS, but I must tell it what type I want. So in this case, list of string comma bool, and I get my original value back. So that's all nice. But now if we have a custom type, we just import data binary, encode and decode. Right, what's the example here? Sorry. Okay. My type AB for that flag bool, combo AA. Sorry about that. Combo AA. Other B and my type AA. Okay, fine. AA. Sorry. Two type parameters. A. Right. And we could, for example, have an example value example. I don't know, my type string int. Other. Now I need an int 42. Or maybe not int, let's say, or whatever. Let's leave bool. So I need a bool, let's say true or false. Int 42, and now I need another my type. For example, I can use combo, and now I need a pair of two strings, Haskell, Java. I mean, the type itself is, of course, not important. It's just something weird. Okay. Okay, fine. And I could do deriving show, of course. Right. But now if I want to serialize that, obviously it won't work. And that will complain that there is no instance for binary. And I also can't derive it just like that because it's not on this list, neither on the list of things you can derive for Haskell 2010, nor is there GHG extension derive binary. However, there is a GHG extension that derives generic. So we'll come to what that means soon. Let me just, first it doesn't allow me, but there is an extension called derive generic. So now it has that. And now I can just do binary. And I need another extension, derive any class. So we'll explain later how, what that means or how that, or what that does. Right. And now I have binary. And if I now reload, so now I can encode my X1. And I can decode BS my type string bool, and I get it back. So that's how you use it. So if, that doesn't work for arbitrary type classes. The type classes must support that. But binary is one of those that they have so-called generic support, and you normally find that in the documentation. So if we let's see, I saw something about this earlier. So here they show how you can do it by hand. That's something we did when we talked about this. And here there's a chapter in the documentation, generic support. And they do exactly what we did. So you need the extension derive generic. They do it a little bit differently. If you don't want to use this derive any class, you can alternatively, instead of writing it here, wait a second. So alternatively, you can also do it like this. Basically write an instance or pretend to write an instance. Right, and then you need the things for this to work. You need binary A and binary B. But then you don't need this derive any class extension. So that was actually the old way. And now since a couple of years with this derive any class, you can do it just like I showed you, like this. So write it with, into the deriving clause, but you do have to derive generic first, or also. So that's how you use it. So that's very nice. Apart from the fact that you also have to derive generic, it's almost as easy as if it was built in. And the cool thing is that this is now no longer like a static list of a handful of type classes that you can derive. That's now open. So if you create a new type class after today's lecture, you will know how to yourself provide this generic support for it. And then users of your library can also easily derive this instances for this without having to write a single line of code. So that's very nice. Another example is where binary is one example. There are many examples. One of my other favorite ones is ASON for JSON encoding. Let me just have to reload. And that works exactly the same. Let me just so here we needed binary. I think it's also called encode and decode in ASON. That's why we do it. like this. And there's the ASIN library for JSON encoding. So if you do any sort of web programming, it's very important or very common to use that. There it is split into two classes. So there's not in binary. If something is an instance of binary, you can do both encoding and decoding, or serialization, deserialization. The ASON module splits it into two classes, one to allow you to serialize to JSON and one to allow you to deserialize from JSON. Right, and now it's just because we already have generic and ASON also supports generic deriving, so it's just a matter of adding those two and suddenly your data type also can serialize to JSON. So I think it's called encode as well. So now we can do encode x1 and we get a JSON representation of that. And I could also, of course, I think it's called decode. I always forget. Right. So that gives a maybe a. So I can try as on decode BS, maybe my type string bool, and gives me just my value back. So it was just a matter of adding those two classes here in the deriving, and it just works. So this obviously can save a lot of work if you don't have to write this by hand, especially because often it's very tedious to do this by hand. And not difficult, but tedious. I mean, specifically in the case of JSON, I must confess that maybe it's not such a good idea to do this automatically because then you don't really have a control about the presentation. So, and often in the case of JSON, you have to like interact with third-party servers, for example. So they expect a certain JSON format. So especially for JSON, maybe this is not so common and you actually do write it by hand. But nevertheless, if you just need a quick and dirty way to like, I mean, if you are in control of the serialization format of the JSON schema, then it's fine to use it.
We have a question.
Yes.
So is generic being used as a normal type class, or is it a special application of deriving?
That is a generic is a normal type class. I mean, what is special is that GHG has support to derive generic automatically. And then what's also special is that generic has support to basically use this syntax here to then make use of the fact that you have a generic instance to derive those instances. But all of these instances, I mean, all these classes here are just normal type classes. So I think it will become clearer when we, when we explain how it actually works. I mean, what generic does.
Yeah.
But it's normal type classes. You could also, principal, write the instance by hand for all of these, or including for generic.
Okay.
Okay. Sorry, wrong slide. So I showed you the example with binary. So this was the old way to do it. More modern ways that you can directly derive it in the deriving class case. Okay. Right. So that's basically how you can use it. So it's really useful. So now let's try to explain it. And I think this is a bad name, this generic program. So let me just move or copy. Whatever. Let's put an example. Let's call it simple. So first we explain the idea, and then we look at GHG generics. What did I call it now? Example and simple. This doesn't exist anymore. Okay. So first, we basically, if GHD didn't have support for generic, we first explain how you could basically do it yourself. Then it's not as convenient as it is now, but we will see. I mean, it would still be useful. And so yeah, let's explain the idea. And as an example, let's start with something like EQ, but let's not use the built-in one. Let's define our own simpler version. So class EQ prime A, where let's call it eq from A to bool. So it's supposed to be equality, of course, but I don't use the prelude class EQ. I have my own version. And the prelude class is also a bit more, I mean, it uses the operator equals equals, and it also has the not equals, but that is not important for this topic. Okay, and let's first define some instances. I just want to see. So let's start with this type T, which can be, has one constructor A and an NTT. Okay, fine. Data T, it can be an A, or it can be, what was it? An NTT. Let me just show just, right. So how would we write an instance for that? I mean, we could derive eq, of course, but now we have this eq prime where we don't have deriving support. So we have to write an instance by hand. So group prime T where? Okay, so when are two equal? I mean, there are two constructors, and for them to be equal, first of all, of course, they must use the same constructor. So if both use the A constructor, they are equal. And if both use the N constructor, well, then they are equal if X equals X prime and Y equals Y prime, which are again of type T. So it's a recursive definition. So it's eq X prime and eq Y prime. And finally, if they use different constructors, then are not equal. So in all other cases, I mean, there are two more cases, they are not equal. Okay, so far so good. To the REPL. Now we could try it out. I mean, eq A is true and eq whatever, N A N A is also true, but eq N A and, for example, A is false. Fine. Okay. Let's look at another example. Okay, that was that choice. It can be int character choice. Where is choice? Okay, fine. Let's see. I mean, these types are just some, I mean, they're not important. It's just so that we have examples. So what was it? Can be I int or C character or B choice bool or S choice. Okay, and again, we can write an instance. So eq prime choice. So again, they can only be equal to choice values can only be equal if they use the same constructor. So eq I n and I n prime are equal, well, if n equals n prime, where this is normal equality. Or we could also, I don't know how it's done on the, no, okay, fine, sorry. Do we have an instance for? We don't have an instance for int yet. Did I overlook that? No. So we do need an instance. Okay, fine. Let me just write it. So recursively, if n and n prime equal. So C and C equal if C and C prime equal. B, C, B, and B, C prime, B prime equal if C equals C prime and B equals B prime. And finally, S C equals C prime. And in all other cases, other constructors, it's false if the constructors don't match.
The slide says assuming instances for int current.
Oh, okay. Okay. It says assume. Okay, I would need. Let me just write it quickly. I mean, it's easy. Instance equal prime int, where I can just use the normal equals this, and now I need for character, I suppose. So for int and character, I just define it as the built-in or the prelude equality.
And Boolean.
Boolean, yeah. Okay, fine. Let me just see whether there's another example. Okay, there's one. But already we see, I mean, hopefully the pattern. So the pattern seems to be if you have several constructors, then things can only be equal if they use the same constructor. And if those constructors have arguments, then even if the two use the same constructor, recursively, all the arguments also have to be equal. And if they don't use the same constructor, then it's anyway false. So, I mean, how many cases does the function have? Well, we have one case for every constructor, and then this catch all for if the two arguments have different cases. And on the right-hand side, we have basically conjunctions where we recursively compare all the arguments with each other. Right. So we have for each argument of a given constructor, we have one conjunct. So what's important is how many constructors do we have? How many arguments does each constructor have? And again, as before, I mean, recursion leads to recursion, and other types lead to invocation of equality on those types. So just to see, I mean, here, for example, we define eq prime for choice, but the eq prime here on the right-hand side is for, I mean, that's for choice. So that's recursively calling because X is again choice. So this here is a recursive definition, and that eq prime is for the B's, which are Boolean. So there we call instances on, I mean, the methods on other instances. So we define the instance on choice by calling the one, I mean, using the one on Boolean, for example, or here we are using the one on int and here the one on character. And here recursively, again, the one on choice. Okay, let's take one more example. Our beloved tree type. Data tree A, so it's leaf A or node tree A. Let's write an instance for that one as well. And of course, I mean, that won't work. We will need equality on A, but let's see. So again, I mean, they must have the same constructor to be equal. So it must both be leaves. And here I need equality on A. Okay, and if it's nodes, then I must compare the arguments to the node constructor. And then I always have this additional case for when the constructors are different, when one is a leaf and the other one is a node, in which case they are not equal. So that's the same, again, the same pattern. We have one case for each constructor. In this case, we have leaf and node, so we have two, plus the one when they are not equal, the constructors, when we use different constructors. And for a given constructor, we have like a conjunction on the right-hand side, where we call the same function on each pair of arguments. Okay, I'll do that right, yeah. Okay, lots of examples, but that's good. So data rows A, we have seen that before, just fork A, rows A. So that's a so-called rows tree, where it's not a binary tree that always where a node always has two children, but it's an arbitrary number of children, including 0 children. So we don't even need something special for the leaves. A leaf is just a fork with 0 children. Again, instance A prime rows A, where? Right, and now, we want to write eq. So, now we actually don't have this. So let me just see how it's done on the slides. Right. So we need to compare those. What's the problem now? Why? Sorry. Oh yeah, sorry. It's XS, and I forgot the actual element. Okay, and now we see that we don't have an instance for lists, so we can write that as well. Instance eq prime A prime list of A, where the empty list equals the empty list, and to have a non-empty list, we must compare the heads and then recursively the tails. And again, if one is empty and the other one is not, then they are not equal. Okay, so what do we learn from this? Let's check. Okay, we have this instance for lists. I wrote that, so we don't have to assume it. Okay, and we see that in these two examples now with tree and rows tree, in our instances, we needed like a constraint. For tree A, we needed that A has the same constraint, and similar for rows. For rows A, we also needed that A has this constraint. So parameterized types like tree or rows often have instances where the where we have constraints on the arguments, and then it just works as expected. So we have now seen lots of examples, and hopefully now we can all see the pattern. So we introduce a parameter for every parameter of the data type. We introduce a case for every constructor of the data type. We have a final catch-all case that returns false. And for the other cases, we compare the constructor fields pairwise and combine them using AND. And for each field, we must use the appropriate equality instance. So that, depending on what types the arguments of the constructors have. So all our examples were like that. There was not a single exception for these. So it's like very tedious. So the idea now is to basically take this slide and convert it into code somehow. So we can like describe it in words. Can we write a program to do it? And this is now so-called data type generic programming. And the key idea is that we represent a type A as an isomorphic type rep A. So isomorphic means it more or less the same if you squint. So it may have different names for the constructors, for example. But apart from that, basically modular renaming, it's the same. And the idea is that, I mean, we have like infinitely many potential types because you can, as we said in the introduction, you can introduce your own types with arbitrary names and so on. But the idea is that we will only use a limited number of constructors for these representation types, only a handful of different constructors. And then we will define functions on these constructors. And then we can use what we do for these representation types to get it back to work on our original type. So that's the plan. And we'll see that as an example now. So the question is, how do we represent types? So some of the ideas, basically, we want to get away from names for constructors. And I mean, that's one of the main ideas. So there's not one good solution. And depending on how you do this, it can make certain things easier and others more difficult. And therefore, there are also like lots of different approaches to do this in Haskell. I mean, one is sort of special because GHC supports it, but there are like lots of different data type generic programming libraries in Hackage. And we'll basically look at one that is very, I mean, that's much simpler, but basically similar idea to what GHC does. So that then in the second part, when we look at how GHC does it, it's easier to understand. And that representation is called binary sums of products representation. Or actually, it should be called binary sums of binary products, but okay, fine. So, I mean, one thing is we must somehow choose, I mean, we have like data types with potentially more than one constructor. So let's first start simple and just look at two constructors. And I mean, two sounds like bool, but bool is not good because, I mean, these constructors can have arguments. So it's not just, I mean, it's not enough to know which constructor. Somehow we also need like the arguments to that constructor. So like the canonical type that does that is either A, B. So you have the choice between two things. You can choose an A or a B, and then the constructor names are left and right. And once you have this binary choice, either A, B, you can also choose between three things without introducing something new, because you can just use either twice. So to choose between A, B, and C, you can choose between either A or either B and C. So once you have like binary choice between two things, you also directly have like choice between two or more things. And so that's the one thing. So for constructors, so we can, if you have something like either, we basically have the cases that we have two or more constructors, or one constructor if you don't use the either. So now for each constructor, I mean, we have to look at the fields, the arguments to the constructors. And again, if we start with two, then basically what either is for sums, for choice, pairs are for the opposite, products, so-called products. So, I mean, this is like canonical type that needs two things, an A and a B. And again, if you have three things, like a triple of an A, B, and C, then you don't need anything new. I mean, Haskell, of course, does have triples, but if Haskell only had pairs, then that would be enough to do something like this. I mean, this is more or less, I mean, it has the same information, an A, a B, and a C. So you just take a pair from an A and a pair of a B and a C. I mean, same idea to the either case for sums. difference is, of course, here you have either an A or a B or a C. And here you have an A and a B and a C. So this now, the either idea and the pair idea allows us to basically handle different constructors and different arguments to a constructor. And then we just need like the base case if there's, for example, a constructor without argument. So how would we do that? We could, for example, use unit. No information. Right, and we could use these types. So we could indeed use pairs, either, and unit. But we will just give them different names. Let me just write this. So this will be our representation types. U, this is like the unit case, then this is like either. We write that with an infix. I'm not sure whether we have ever done that before, but I mean, that's possible in Haskell. So like a type constructor, it doesn't have to be like either in front of it can also be infix. It then needs a colon in front. So we will use this instead of either, but obviously it's like the same thing. I mean, isomorphic, just a different name. Instead of either, we call it colon plus. And instead of left and right, we call it L and R to make it shorter. And instead of pairs, we will use this colon star and again use this. So, I mean, I can just define that. I mean, of course, we could choose other things. It's just, I mean, and it's anyway only for this lecture because GHT does it slightly differently. I think I need an extension for that type operators or something. Yes, so you can only use these infix type constructors if you have an extension called type operators. So I activate that. And what was the last one? Okay. So now we could do, I mean, we could write things like, I don't know, C star right true star U. Could define.
You need to define the function, the star function.
Sorry.
Did you reload already?
I thought so, but maybe I didn't save.
Oh, defaulting. Okay.
But why? What? I thought that should be clear what the type is. So why? What is it defaulting? I'm a bit confused now.
Show A0.
Or the A. Oh yeah, yeah. Because I didn't. I mean, it doesn't know what the L is, what the A is in this case. This R true. So yeah, yeah. Okay, fine, fine. Anyway, so that's that. And now, of course, that's until now quite abstract. So now, of course, we want to see how that is useful and how actually these types, how they are equivalent to these things. I mean, what we mean by representation. So let's start with bool. How would we? Let me just. Okay. Right. So I think I do just the type. So now we can define our class generic. So this is now not the like the built-in. This is now our own. So we say type is generic. So first of all, we have an associated type. I talked about that when we talked about monad transformers. Remember, I said there are like different ways to do this monad reader constraint. And in the end, we ended up using functional dependencies, which is done in the MTL library. But I said that there are alternatives, and you can also use these associated types. So a class can't just have methods. Functions can also have types. So we call that rep A. That's just type. But of course, that's another extension, type families. Yeah, and there I should write type. Otherwise, it's always complaining. I mean, in the old days, we used the star, but that's somehow getting out of fashion. So instead of star, I write type. Okay, and now, I mean, okay, fine. So some type is generic if we have a representation type. Now we don't write that here because we can't, but the idea is this rep A will only use these things. So rep A will either be a U or it will be using this plus where A and B are again of this form, or it will use the star where A and B are again of this form. We can't express that here, but that's the idea. And then in addition to that, we have a from. So we can convert between a type and its representation type back and forth. And again, we can't express this. The law would be that if we go back and forth from and to or to and from, it's the identity. So that's what we mean by isomorphism. So we have another type, rep A, which is isomorphic to A in the sense that we can go back and forth between the two. And then the composition from to or to from is the identity. And okay, and again, the plan is, I mean, what would that help? I mean, we could, of course, always use rep A equals A and then have from and to the identity. I mean, that would be a trivial instance. But the idea is that this rep A only uses, as I said, these three constructs here. So let's start with,
And
yeah.
yes, we have a question. In this case, the star, the colon star colon operator represents a pair.
Mm-hmm. Yeah, I mean, it's isomorphic to a pair. As I said, I could have used here instead I could have used unit. Here instead I could have used either AB, and here instead I could have used A comma B. So that would have been just as good. I could have used those without defining these new ones. It's just sort of tradition or like more compact to define these new data types. But I could do exactly the same, not defining these new data types and just saying my representation is supposed to just use unit, either, and pairs. So this is not the same as, I mean, it's a new type, right? But basically it's isomorphic to pairs. It has the same information. It behaves like pairs. I mean, a pair has an A and a B. A value of a pair, A comma B, is a value of, is something of type A and something of type B. And the same is true for this one. I mean, value of type R star B is something of type A and something of type B. So let's look at a couple of examples before we have a break to just make that clearer. So for example, bool. So instance generic bool. So first step, we must write what the type, the representation type is. So the idea is that, as I said, if we have several constructors, we use plus to switch between them. So in the case of bool, we have two constructors, so one plus is enough. So we have something plus something. So now what's this something? So the one is the true constructor of, I don't know in which order it's here. Okay, fine. So false and true. And so now here we must somehow encode the arguments, the fields of the constructors. But false and true don't have any arguments. So therefore, both are U's. U. So that's the representation type of bool. And now, of course, we need this from and this to. So somehow we must be able to convert a Boolean to this type and from this type. So I must say what from false is. I must say what from true is. And I must say what, I mean, must define two as well. Okay, now, of course, I mean, it's not, I mean, I could pick left or right, but let's say that false will pick the left one. So that's LU and true is right U. And now, of course, I also need two. So two from rep bool to bool. So two, I mean, it's plus, I mean, U plus U, and this plus has two cases, L or R. So I can have an L, and U only has one. So, I mean, I could do this, or I could also do this. It's the same. So it must be compatible. So, I mean, I must go to false here. And to R, U is true. Right. So that's our first instance. We can, if we like, we can try it out. I mean, we can say from true, from false. And we can also say we can't, but yeah, I mean, I suppose what happens if I do 2 LU? Yeah, okay, fine. So we can also go back. And obviously, I mean, it's the identity if I go back and forth. So that's like a boring example. Let's look at lists. They are more interesting. Generic list. Where? Right. So type rep. So for lists, again, I have two constructors, the empty list and the non-empty list. So the representation type will be something like this. Then the empty list constructor doesn't have any arguments. So that's U. Now the cons constructor has two arguments, the head and the tail. So that will be a pair because it's two arguments. Okay, and the head has type A and the tail has type list A. And we notice a couple of things here. I do not require that A is generic. And I also don't like, I mean, if I required that A was generic, I could write something like rep A here or so, but I don't. So I basically only unravel one layer of the constructors, and then I leave the A's and the list of A's as they are. So it's so-called shallow representation. Right, and I need the from and the to. So from, I have a list of A's to rep list of A's. So two cases, the empty list. So I take this left U there, U. And if I have a non-empty list, so cons, so I take the right. And now I need this a star, so I must give head and tail. So it's head and tail. And two, so from rep list to list. So again, two cases because of the plus. So I can have a left U, which I map to the empty list, and I can have a right a star, or and that of course I map to XS. So I can whatever from Haskell. Right. So as we see, it's not deep. It only like handles the first constructor, not the recursive. It leaves the recursion untouched. So it just unravels the first constructor. The first constructor of Haskell, because Haskell is a non-empty list of characters. So it does have a head and the tail, and it just tells me, okay, we are in the second case, the non-empty case, and the two arguments are an H and Haskell. Right. Let me see. I think we can do one more example. So in particular, because of that, as I said before, I don't need a generic A constraint here because I'm not recursively calling this from and to. These are not recursive. Okay, tree. I mean, we can go through all our types if you want, but let's at least do tree. The same thing. So instance generic tree A. So again, we have two cases. So it's again a plus between the two constructors. I must definitely do at least one example with more than two. I'll do that next, and then we can have a break. Okay, so okay, and the leaf case now has one argument of type A, and the node case has two arguments, so it's a star, and the arguments are both tree A's again. Okay. Yeah. Okay, so if I have a leaf, I send it to the left. And if I have a node, I send it to the right. The two arguments are X and Y. And two. Okay, if I have a left, it's a leaf. And if I have a right, a pair, it's a node. Okay, and let me do, no matter what is on the slides. Okay, let me see. Yeah, okay, but I want to, I can do this, but let me nevertheless do something with three constructors first. We have an example that has two. Okay, this choice thing, I mean, this may be a bit tedious, but nevertheless, let me do this. And let me just first write it here, because then otherwise I forget what the constructors are, or rather here. And I can copy it down later. So instance generic choice. Okay, now we have 1, 2, 3, 4. It's somehow up to me so I need like lots of pluses now. So I can, not sure whether there's a, sorry, plus. So this is the, for I, so now the rest is CBS. So now C, sorry, now B and S. Okay, now the first one, the I has an int as argument. The second one, the C has a character. The third one, the B has 2. So here I need a star. Where the first is choice and the second is bool. And finally, the last one has choice. Okay. So I need from app choice. Okay, now I must concentrate. Okay, fine. So if I have an I, it's left. If I have a C, I must first go to the, here I must go right. And then I must here, it's in this one, it's the left one. So L, C. If I have a B with a C and a B, I have to go right twice and then left. And then I have the star, so I have the C and the B. And finally, if I have an S, must go 3 times right, and then I have my C. Okay, and the other way around. I hope by now you find it boring. That's exactly the point. It's so boring that the compiler can do it. Not for us, not this one, but for the like real generic, this is done by the compiler with this GHT extension derived generics. Okay, fine. So yeah, it's basically the same, the other way around. I don't know why my editor keeps doing that. Right, left. E. Finally, right, C is SC. Okay. I don't know. Maybe it's even better to leave it up there. Yeah, close to its type. Yeah, and I promised a break, but I think there's only one last example here. Right. Yes. So
you have
let's
the
do the
example.
rows. I'm sorry?
I'm sorry, but you have the example one if you want to do the from and to. You have already
For choice,
yeah.
was that choice?
EX1, I think, wasn't.
Know what you mean? Was it?
Oh, maybe it was the previous.
No, that was this other type, this weird my
Sorry.
type. No, it's fine. Actually, that's a good point. I should actually, I think we can just take it slow. So let me just copy that to here as well, and let's do that as an example as well. And why not? Forget about this binary stuff for the time being. Yeah, let's do this as an example as well. That's a good example because it has two type parameters, and we don't have another example with two type parameters. So yeah, thanks for that. So what's now? So we have 3 constructors. So we need 2 pluses. Okay, the first one takes a bool. The second one, yeah, well, this is now, debatable. I think. No, I think it's not. We have to. We could say it takes 2 A's, but I think we must actually say it has one argument of type A, A. to do it mechanically, basically. So this one is an A, comma A. And the last one, okay, this is interesting now. This is really a good example. That should have been, yeah, anyway. Because this is now the first example we see where something has 3 arguments, so we need like 2 stars. So this is now first argument and then second, third. Okay, the first is B, second is int, the last is my type AA. Okay, and now from my type AB to rep my type AB. Okay, so in the first case, if we have a flag, we choose left. If we have a combo of a pair, we choose right, left that pair. And if we have other consisting of a B, an int, and another my type, it's right, right, and now B star N star X. And now Robertino is right, of course. Now we could do from X1. Right, and would be, so this RR picks the third constructor, and then we have the 3 arguments, false, 42, and combo Haskell Java. And again, it's shallow and just one layer of constructor unraveled. Why is it still complaining? Oh, because I don't have the 2, sorry. So 2 rep my type AB, my type AB, 2. Okay, if we have a left, then it's what's it called, flag. We have a right, left of a pair. It's combo. And if we have a right, right of a B, an int, and another my type, then it's other B N X. Ha. Right, and just let me do rows, then we are done with this chapter. Right. I think it's actually a better idea to write it with the types. I should have done that before as well. So let me write it here directly. So instance generic rows A, where? Okay, so here we only have one constructor, so no plus. So it's just one constructor, and it has 2 arguments, one of type A, one of type rows A. So we just need 1 star. So it's very simple. It's just A star list of rows are A. So 2 from fork A access, just A access, and 2 of X A, that's just fork A access. Right. So yes, we can have a break now. So I just hope, and of course, I mean, now then after the break, we explain what this is good for. But now we have a bunch of examples. And I hope you agree that once you have seen all these examples, it's very mechanical So you could imagine that like Simon Peyton-Jones or whoever implemented that in GHC can basically extend the compiler to do this automatically, because it's completely mechanical. You just, for each constructor you have, I mean, for each additional constructor you have a plus, and then in each constructor you just check how many arguments there are. If there's none, you use the U. If there's one, you use as is, and if there's more than one, you need stars. So it's completely mechanical, these instances. And also you see, I mean, this was also very boring to write this from and to. I mean, basically the from and to, if you look at it, like it's just basically flipped the two sides. Always like as if I just swap the left and the right hand side. So it's obvious. I mean, it's very boring to write, and it's also obvious that this law is that if I do from and to or to and from, it doesn't change anything. If I go back and forth, I end up where I started. Okay, so let's have a break, maybe until, I don't know, 40.
Okay.
Okay.
Yep.
Except if there are questions now.
Not yet, but feel free to ask questions during the break.
Yes. Okay, then we'll talk again in like a bit more than 14 minutes. Okay.
Yeah. Let's do it.
Let's do it. I'm sharing again. Right. So now we have gazillion of examples for this generic. And note that we didn't write generic instances for primitive types. I mean, we had this one lecture that int is not really primitive, but for our purposes now, these things like int, character, or float are primitives. So we can't derive any generic functions for those. And if we want something to work with these types, we have to do like special cases manually. Okay, so now that we have this stuff, this generic class, how do we actually use it? So let's come back to our equality example. So we have defined this class generic that maps data types to representations that are built up using these three type constructors, U, plus, and star. So the idea now is if we can define equality on those three types, then we should be able to basically get generic equality for everything that's an instance of generic. So let's first define a class for this. Let's call it GEQ. And it's very similar. So let's call it GEQ and A2 bool. So it's basically identical to our EQ prime class. Okay, and now let's write instances for our three constructors. So the U, the plus, and the star. Let's start with U. GEQU. Well, when are two U's equal? Well, they're always equal. So GEQU equals true. I mean, there's only one possible value in U, namely U. So, I mean, and that value is equal to itself. So that is easy. So now let's do plus. Okay, fine. Let's first write so this is now the case where we have, I mean, our recipe earlier was if we have several constructors, then two, and in this case we have several, let me two, L and R. And we said that in that case, two elements are equal if they use the same constructor and the arguments are equal. So if we have an LA and an LA prime, then they are equal if A equals A prime. And now I see this is now for A, so I need constraint that I have equality for A. Similar for B, so if both use the right constructor, then they're equal if those are equal, those arguments. So we also need generic equality on B. And in all other cases, we always said if they use different constructors, then it's false. And finally, we have the case of several constructors, so 2, because we only have this star. So star B, where? Well, there we said if we have more than one argument to a constructor, then all of them have to be pairwise equal. So GEQ A star B and A prime star B prime. We need that GEQ A prime and GEQ B prime. And again, we need GEQ on A and B. So again, we have this constraint. GEQ A. And that's it. So we have these 3 instances. And we only need those 3 because they handle all our cases, the U, the plus, and the star. So now we have it for all of this shape. And let me just, what primitives did I have? In character bool. So for primitives, in this case, I would need to write it by hand. So instance GEQ int, where, but I can just use built-in equality. And I can do the same for character. What was the other one? I think bool, but bool I don't even need because bool is not a primitive type. Right, so bool, this one I don't need. Okay, and now the idea is, so now how do we assemble this? So now we can define a default. So if we can define a default equality. So if we have a type that's generic, and if the representation is an instance of GEQ, then we can compare 2 A's for equality. And how do we do it? Well, we just use from to get from A to rep A, and then on rep A we use GEQ. There's something wrong there. Okay, fine. Okay, and now we can or this T, I didn't write generic for T, I think, or did I? I think not.
No.
So let me add that quickly. So instance generic T, where type rep T is, okay, 2 constructors, so we need a plus. The first constructor has no argument, so it's a U. The second one has 2, so it's a star, 2 T's, so star T. T to rep T from left constructor is the left U. From right constructor is right x star y. And 2 rep T to T. 2 left U is A. And 2 right xy is n. xy. Sorry, it's a star. Okay, right. So now these instances that I had to write by hand, now I can just just use generic equality. So I can just say eq equals default eq. Why is that now not working?
You're in file, or because you're in sample now.
Oh, there must be. Oh, sorry. So I must have made a mistake somewhere. No, no, I'm in the right file.
Yeah, what's the error? Sorry.
That I don't have. Oh, instead of GEQT, but why would I want GEQT? It's a bit confusing now. Just saying, because I said GEQ rep A, generic A, GEQ rep A. I'm a bit confused.
You need to constrain GQA, I think, in the when writing.
No, I mean that's exactly the point, that I need generic equality on the representation type. A must be generic, and then I need generic equality on the representation type. Something is off. Just saying. I think no. Just
You have generic equality on the representation type, but not in the type. I think you need to constrain that A is a generic, has the generic equality constraint, right?
no. I mean, no. This is always representation types. One second, let me just see. This is exactly how I have it, isn't it?
Yeah.
And also the GEQ is right.
But if you keep going, we have the actual.
Ah. I'm a bit. No, so, right. Sorry, I'm confused because there's a different notation here. No. Sorry about that. But now I'm really a bit confused. Let me just delete that for a second. Need a key. Okay, fine. That can. So what's the type of default equality? My T. Um, right, and yeah, I think hmm, yeah, I think the problem is not at the top level. The problem is here that right. Um, yes. Okay, fine. I was confused. I mean, if it tries to do this now, what I tried there, so it tries it for T. So then this must be GEQ. And plus is GEQ if U is GEQ, and this is okay. So U is GEQ. So it checks this. And star is if both are. And then it needs GEQT. GEQT, not EQT. So that's the problem. So what I should have done here now is instead GEQ T, and now it's called GEQ. Now that works. Okay. Yeah, that was the problem. So again, sorry. I mean this default. Sorry about that. So the default EQ, it says I can compare two A's for equality if A is generic and if I have generic equality for the representation type. Okay, so and I tried this for T. So and T, the representation type is this. So we have an instance for GEQ for plus if we have instances for the two sides. We do have an instance for U, so that's fine. So we need an instance for this. And we do have an instance for star if we have an instance for both sides. So we need an instance for T, but we didn't have an instance for T because that was a different class. So if I want it recursively, I must use the same class. So it must be GEQT. Right, and same for all these others. So now I can basically change all of that. And I already did the int and the character. Bool, I now don't need to do anything. I mean, it's not primitive anymore because I have a generic. That's GEQ. Right. So now we don't need, I mean, for choice, we get it. GEQ equals default eq. For trees, we have it. For rows, we should have it. Good, but what's the problem there? Lists, but this is here now. So now the error here also went away. And that's that. Is this my type? So we can do it for my type as well. Instance GEQ my A, GEQ B, GEQ my type, A, B, GEQ is default equality. What's missing now? Pairs. I didn't write an instance for pairs yet. So let's fix this quickly. I don't know where, anywhere. Here. So I need an instance generic for pairs, A, comma B. So the representation type of pairs of A and B is, of course, A star B. From A, comma B is A star B, and to A star B is A, comma B. What's that now?
The type keyword.
I'm sorry?
The type keyword. No, you're missing the type keyword at the beginning.
Oh, you're right. Sorry, you're right. Type keyword. Okay, so now actually this should also, where was that problem? My type, because of the pairs, yes. So this should, what's now? Okay, fine. GEQ, then I also need. Was I here? So instance GEQA, GEQB, GEQA, comma B, where GEQ is default. Okay. So now my type should work, yes. Okay, right. So that's that. Let me just check. So that now works. So we can do these things. We can also instead use another extension that we haven't looked at yet. That's called default signatures. So if we do that, so where's our GEQ type? It's all a bit, sorry. It's all a bit right. So there is something, I mean, we have seen, I mean, what we have seen before in for example, in the actual EQ class was something like this, that you can do like default implementation. So I could do something, whatever. I could write x, y equals false or something. So that would mean that when I don't actually write the method by hand, then this would be used. Of course, I don't want to always give false or true. I mean, what I want is to say default EQ. Okay, but then I have the problem that, I mean, this has the constraint, that A is generic. And so this extension does the following. It allows me to give like constraints for this default implementation. So I can say default GEQ, and now I can give constraints. So for example, generic A and GEQ rep A, bool. And that complains because I need this extension, default signatures, and now I can write this. And that now means that it's okay to basically not implement this GEQ, and then it will use the default implementation, but of course it will check the constraints. So now I can go through all my instances again and don't need this anymore, because now I have these default instance. Suppose I should have arranged that differently, but fine. Okay. Right. So that's that. And I think I could even do something like automatically just derive it now.
Yeah.
I'll probably.
I think you.
Yeah, I need this derive any class that I said earlier. And now it will probably complain because I have duplicate. I mean, I have this line as here. So now I can delete all of them basically and just do it with deriving. So we had this for T. So I can just I had this one. Well, there I can't really because I mean I don't have access to the code. I mean that's somewhere in the prelude. But I mean I can do it like this, and I think I can also do this. I don't need the where keyword in this case. Okay, here for choice I can do it. GEQ. I must delete this. I mean, bool is the same thing. I don't have access to the source code. For trees, I can do it. For rows trees, I can do it. No, that was the generic instance. Here. I can, if I want, leave the where. Okay. Was that it? My type. Oh, I did that there already. Right. Okay. Yes. So this is cool. I mean, relatively cool. So basically, we have this deriving mechanism now available for our own GEQ, even though I mean that's obviously not built into GHC. So just a combination of this derive any class and that's exactly what it does. Derive any class basically assumes that everything has a default implementation, and if it doesn't, it would complain. That I mean, it will check that, of course. So that's how this derive any class works. So there are different ways to write these things, but yes. So now our GEQ is basically it's almost like a built-in. I mean, as if support for deriving this was built in, and we just get it more or less for free now for more or less arbitrary types, provided we are able to have a generic instance for that. So are there questions at this point?
Not so far.
Okay. So I think we did that. There's also a last, instead of what I did instance, blah, 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 you can also write deriving instance. I think I mentioned that when we talked about GADTs last week briefly. In this case, I don't really see the advantage of doing that. Anyway. Right, so that's that. But now, of course, the question is, have we actually gained anything? I mean, before, I mean, the motivation in this example was we had this tedious work of implementing this eq prime class for all our types, example types. And that was tedious because it followed a very mechanical schema, always the same thing. I mean, one case per constructor plus an additional case for different constructors, and then for each argument of a given constructor, check the arguments one by one and end it all together. And then we said, okay, that's tedious and boring, so we want to automate that. But now instead, we had to have this tedious and boring task to implement this generic instance for all our types. So we replaced one tedious and boring task with another tedious and boring task. But the point is that we only have to do that once. I mean, now, once we have written the generic instances for our types, they are there, and we can use them not just for generic equality, but for all sorts of stuff. So it's this one class that rules them all, basically. Once we have that instance, we can use it for all sorts of purposes. And we don't even have to do that by hand. We could have compiler support for this specific one. Not for, instead of adding all sorts of special cases for special types, classes, or whatever, deriving support, we can have just deriving support for our generic class. And if GHG could automatically derive that, then we wouldn't have that boilerplate anymore. And by having this generic, we could do all sorts of things. So instead of having to implement, like changing the compiler to add more and more like classes that work with deriving, we only have to add this one single case, generic, and everything else in principle can then be done by just providing instances for these three cases, the U, the star, and the plus. And then it automatically works for everything generic. Right, but I think we still have enough time. So in order to motivate that, I would like to give a second example, just to show you that now that we have these instances for generic, we are basically done. And I just want to see how to do that. Right. Maybe that is also a nice reminder of MTL. So let's do this. I hope I still have enough time then in the end for the right. So basically I want to do binary by hand. But not exactly like that. Let's do something else. Let's say, I don't know how to call it, SER for serialize. And let's say I want to serialize and deserialize in one. So serialize. Let's say instead I want to go to bit streams, okay? And I represent bits as booleans, so ones and zeros. Okay, so I want to serialize an element to a list of booleans and deserialize. I could of course write something like this, but I think that's difficult to implement. It's easier if we do something like this, and this is now where MTL comes in. So basically a parser of A. And let's define a parser, new type parser. A as parser. And okay, what do I need? I need, sorry, state T on the state is the remaining token stream, so the booleans. Right. And the monad is list. So I must import this. Okay, so that's the state T transformer. The state is the unconsumed tokens, so the unconsumed bits, and the base monad is lists because I need this indeterminism. Right. I hope Okay, and we did say in the lecture on monad transformers that, I mean, when we did the parsing lectures, we wrote a monad by hand, but that we could just have used MTL, state T over list. Right, and now to get this actually deserialized, okay, let's first write a run parser function. I told you that one always does that. So given a parser A and a list of booleans to a list of results and unconsumed tokens. So run parser x booleans. So I do a run state t x bs. I must import this. Yeah, can eta reduce. Okay, and now, yeah, fine. Right, and now I want my serialize as well. I mean, the original one. So how would that work? So if I have SAR A and given a list of booleans, I want a maybe A. So serialize BS. So what do? I run parser deserialize prime on my byte string. And it succeeds if I have a unique result and all tokens are consumed. So if I get one result with one A and the empty list, then it's a just A. And in all other cases, I fail. What's the problem there? Oh, deserialize, sorry. Okay, so that's my setup. And I mean, it's a bit, with this idea, it's a bit tedious to write it for ints and characters. So maybe we don't do that, or maybe if we have time and feel like it, we can do it. So let's just get a feeling for that, how we would do that. I mean, this is now a bit ad hoc. I hope I manage. I mean, it would be nice to have instance for int, but that's maybe a bit tricky. I can think about that. Anyway, let's start simple. So let's try to do this for our special classes here. So we need it for the U, the plus, and the star. So instance ser U where? Okay, so how do I serialize a U? Well, seeing as it doesn't contain any information, there's only one possible value. I don't need a single bit of information. I mean, I know it's a U. I don't have to waste a bit on that. And deserialize prime. Well, if it's, so let's see, how do I write this now? I mean, in this case, I could just do it, yeah, by hand. I mean, it must be okay, fine. So, okay, I can do it by hand. So it's parser and given, hang on, maybe I shouldn't do it by hand. And sorry, I'm doing this one. So I should derive functor applicative monad state cool. Need to import this. And I need generalized new type deriving, as what I also explained. Okay. This is also good that I did that now so that you see this. So this is sometimes a problem. Now I have like two ways. I have derived any class and generalized new type deriving, and they conflict. So I don't know which is which. There's yet another extension that's called deriving strategies, where you can make explicit how you want to derive something. And that works as follows. So you, after the deriving, you can say new type. Then it uses new type deriving. So it uses the instances coming from the rep type. You could write stock. That's the built-in derivation like show and read. Or you could say any type. I hope this now, not everything else is crashing. No, I think it's okay. Let me just see whether everything still compiles. Of course not. Okay, fine. So far, so good. Let me see, do I need anything else? No, I think it's good. So in this case, so deserialize prime. I mean, I don't have to consume anything. I just can immediately return u. Okay. So now let's do, I think the second easy part is star. So if A and B are serializable, then I claim that A star B is serializable. Okay. So, and I serialize them by simply serializing A and concatenating it with serializing B. Okay, and deserialization also easy. I mean, I just written applicatively, I just sorry, it's prime. That's prime, deserialize prime. Okay, and the most interesting case is plus. Because now, I mean, if you think of deserialization, somehow when I deserialize, I must know whether I'm trying to pass an A or a B. Actually, I think this is probably overkill what I did here, because in this case, it's all I don't need this choice, I think. But I'm probably a simple state T monad would have been enough. I think so, actually. Actually, let me simplify this. I think I only need state T. I don't need the lists in this case. Sorry, but it doesn't change anything. So the only difference is this is now a run state. And now, of course, it's not lists anymore. It's just a pair of an A and the unconsumed tokens. And now this is also simpler. This is just, right. I think everything else is fine. Yeah, that was overly complicated. I don't need the full power of parsers for this, I think. Okay, let's see. Right, so the idea here is that, I mean, in order for when I deserialize, I must know whether I'm passing a left or a right. And the idea is to basically give a marker first, so one bit that tells me whether it's a left or a right. So serialize a left A. I just, for example, start with a 0 bit and then serialize A and serialize a right B. I start with a true and then serialize B. Okay, and to deserialize, I I check the state. Now I need, right, I'm sorry about, I'm very sorry. I think I do need the lists after all, because I can fail, of course. Yes, and there's no way to fail at the moment. I mean, I could use an except T, of course, instead. Sorry about that. But I think it's no big deal. I mean, the code is, as I said, the same. Just the monad is different. And just this is different. Right. Okay, fine. So what do? I check the state, so the unconsumed bits. So now I need my state monad. Okay, and now of course, if it's the empty list, then I'm failing, right? Because I mean, I need this first bit, 0 or 1. So if there are no bits left, then something is wrong. So I must basically return the empty list, and because I'm in state T, I must use lift to get from the list monad into the state T monad. And if I do have a first bit, so if it starts with false and some other bits, I put the other bits back, and then I know I have the left constructor. Okay, and if it's true, if it starts with true, I put the other bits back, and I know I have a right constructor. And it's a prime. And now I need all sorts of imports. Right, I needed monad trans as well, sorry, where I defined my parser. Monad state, monad trans. I must write an instance, or I can parser. Okay, that's not very pretty, but it works. Okay, right. And that's our 3 instances. So, I mean, it's actually very compact and simple, right? I mean, I know if I have something with no information, I don't have to waste any bits on it, and I know the result. So serialization, deserialization is trivial. If I have like 2 things, I just do it in sequence. First serialize the one, then the other. And for deserialization, same way. I deserialize the first and then the other and reassemble them. And the interesting part is the sum case, where I have the choice between a left and a right. And that I solve by using 1 bit to indicate whether I'm left or right. And then when I pass it, I check. I mean, I fail if there is no bit, and if the bit I find is false, then I recursively pass the rest and add the L constructor, and otherwise I recursively pass the rest and add the R constructor. Right, and now the only problem is that it's a bit difficult to try it out because we don't have instances for primitive types. So actually at the moment we can only try it out with bool, for example. But I mean, what do we have? Do we have interesting types? So for example, a tree of bools. So let's say, yeah, and now of course I can write my, so now we have that. Now I can write my default serialization. So if I have generic A, or actually I can now, sorry, I don't have to do it like that. I'm here where I have my class. I can now just provide default implementations. So I hope, so default serialize. So if A happens to be generic, and if I have an instance for the representation type, then given an A, I can produce a list of Booleans. By doing what? Well, I just serialize from X. And of course, I can, sorry. Right. Okay, and what do I do for deserialize? Hopefully the same works as well. So default, if A happens to be generic, and if the representation type is deserializable, then I have a parser A. Deserialize prime. Okay, so what do? I mean, I do have a parser of the representation type, and it's a monad, so I can just, I mean, I have a parser of rep A, and I want a parser of A. But I have something from rep A to A, namely 2, so I can just fmap 2. Right. Okay, and now we should be able to like just derive this for other types. So let's see. For example, I mean, my type is bad because there's this int. We don't know how to do int yet. Tree should be fine, I think. Where's our tree here? So I think I should be able to do here. Okay. Right. And now, so that works. I can just automatically derive it. Now I can have an example tree. I mean, at the moment, unfortunately, it only works for like Booleans, for example, or like, let's try a list of Booleans. Then I need it for lists as well, but I can do this. So let's take a node where the one child is a leaf, true, false. And the other child is another node with 2 leaves. One is the empty list, and one is list true, for example. So example tree is this thing. And now I can't serialize it, I think, because lists, I don't have an instance for list yet. So it will probably complain, yeah, no instance for list of Booleans. So let's write one. Because I don't have control over lists, I must do this like standalone. So instance, if A is serializable, then lists of A's are serializable. Just like that, that's accepted by the compiler. And while I'm at it, I can also do for pairs. I mean, I don't need this now. Okay, and now, oh yeah, for Boolean as well, of course. Sorry. I mean, that we can do it automatically because we have a generic instance for it. But of course, I also don't have control over Booleans. Okay. And there is this tree serialized as a list of Booleans. And of course, the proof is in the pudding. So let's, so that, and now I can try my deserialized PS. So that should be a maybe tree list of Booleans. And tada, I get my original tree back. Of course, it would be a little bit more work now to write instances for int, for example. I mean, if we in the end still have time, maybe we can do this. But I mean, it's also possible, of course. I would first do something like bytes. I mean, and use the binary representation. and then do like word 16 and word 32 and word 64, and then use that to write an instance for int. So there one would have to work a bit. Then you also would have it for character via to enum and from enum. And then you're basically good to go and have it for everything that you're interested in. But yeah, I just wanted to give a second example. So, I mean, because the benefit of generic programming wasn't so clear, I think, after this EQ example, because we still had a lot of machinery and work. And I mean, it wasn't much easier than just doing it by hand. But now, I mean, the point that I made now was once we have these instances for generic, now I could basically on one screen do basically add generic support for, it's really basically just this. So I defined the class, handled the 3 cases, and then I can just derive it for everything like trees. So it would also work for rows trees, of course. X rows. Let's say rows pool. X rows is whatever fork true. Fork true empty list. Fork false. Fork false empty list, and fork true. Fork true empty list. Fork false empty list, let's say. Okay, fine. And now where was the rows tree defined? So I should just be able to automatically derive seer instance now, just like that. And now I can serialize X rows. And deserialization maybe rows pool gives me my original tree back.
We have one question about
Yes,
this serialized example. Could you
yes.
could you explain a bit more on how this kind of serialization is useful?
Well, I mean, sure. I mean, you have to serialize stuff all the time. For example, if you send cat videos if you upload a cat video to YouTube, you have to serialize your video and send it over the network, and the network only understands ones and zeros, bits. So you have to convert some data to streams of ones and zeros all the time and deserialize them again. And I mean, of course, on Haskell, on Hackage, I mean, we looked at this binary package, which does it, but binary uses byte strings. So yeah, and I mean, the only difference is now I'm using like lists of bits. So it can also be 3 bits. Doesn't always have to be 8 or 16 or 24, which is probably not very useful, but nevertheless, I mean, it's just a binary serialization format. So I could just pad it with whatever. I mean, I could like write this as a binary file. So it's a very compact representation of data. I mean, it's not human readable, but it's compact, more or less. So, I mean, you just serialize arbitrary data, more or less arbitrary data, into streams of ones and zeros. And then you can send them somewhere via the network or via the internet. Does that answer the question?
We have another one. What from the same person? Why do you call the bulls bits? Ah, okay. So yeah, I think there's some misunderstanding on the representation of
Yes.
bits as booleans. Yeah.
Yes, I could, of course. I mean, obviously I could have defined data bit, whatever high and low.
Or 1 0 in.
Or 1 0. Or 0 1.
Yeah.
And then instead of booleans, I could have used bits everywhere. I was just lazy and wanted to use a data type that already has 2 values. Something that's wrong. Still, I don't know why the get is. The problem with the get now. Somewhere there's still a, oh yeah, here.
Oh, yeah.
Sorry.
Yeah. It says that thank you. It now understands.
Okay, good. Right. Yes. So I just wanted, first of all, I think the example is nice, and secondly, the I mean, it reminds us of the parser lecture, and it reminds us of MTL. So yeah, I just wanted to do this quickly. And it shows, I mean, now really basically on, I mean, more or less on like one screen or two, I now have like a type class, a useful type class, the serialization, and have generic support for it. So that then people that want to use this type class, all they basically have to do once they have derived or implemented generic somehow for their type, they can just edit. I mean, I could do this everywhere now, of course. I could add my serialize. The problem here is now it complains that I don't have an instance for int because of this int here. So therefore I can't do it here. But I could write an instance for int. Here I also can't because there's also this int lurking in there. Yeah, so if I had more time, I would write an instance for int, and then I could do all the other examples. Okay, so I think we should probably have, I'm not sure. I mean, now the last topic is how GHG actually does it. So maybe we can have another short break until 50 maybe, and then do the rest with how GHG does it.
Yeah, sure.
Okay, then let's have a short break again. Right, so let me copy this to something, I don't know how I call it, GHC. GHC. Reload. GHC. Just delete this. Probably some of that we will need again. No, let me keep this. Right, let's first, but let's delete our generic stuff now. Let me just get the tree type. I clean this up later. And just get rid of these things. Let me comment everything. Right. Not right. Why? Did I? I didn't remove that again. Okay. Problem was that I didn't have int. Okay. Right. So if I open the REPL again, first again, this simple model briefly. I think I didn't mention that. So we have this, I mean, we had this thing's in the way. Just a second. In this generic, we had this associated type with type rep. And I showed that briefly before, but if you want to look at the definition, you can do that in GHCI or in the REPL with colon kind exclamation point. So for example, I can ask for the representation type of tree int, and then basically it tries to, if that type exists, then it shows me how it's defined. So that was our representation type for a tree. So now let me load GHC. And in GHC, we can derive generic automatically. So that's a GHC extension. But for that, first I must get it into scope. So that's in GHC generics. And I must activate this extension derive generic. So now we have that. And reload. And actually, I can ask for information on generic and see there are lots of instances. And we see here, there's actually, I mean, so far so good. We also have this representation type, and we have from and to. So in that sense, it's similar to what we did. But now for the shocker, if I now ask for kind prime tree, rep, I think I must import sorry. No, let me just do this again. Load GHC. Let me just, sorry, it's easier if I import all of this now. Right. So now it looks already less intimidating, I think. Yes, so we have this rep, we have from and to. Don't look too closely yet. Okay, now if I now ask for the kind of rep tree int, then I get something horrifying. So I get this. And that's, of course, a far cry from the simple thing we had. Let me switch to the slides. So with derived generic, we get that automatically. So this was our version. Actually, in GHC, the first difference is that the representation of A is now no longer of kind star, but it's a type constructor now from star to star. For some like historical reasons. So from is now from A to rep AX for every X, and to is from rep AX for every X to A. So that's the one difference. Right, it's a pragmatic choice. So some things become easier, but we can sort of ignore this extra argument. And the worst part is that it looks so much more complicated. But I mean, this was ours, and this is GHG's. But if we squint, so we still basically see the same structure. So we had this A and then a plus and then 3A stars 3A. And all of this is still somewhere in this mess. There's just a lot of stuff in addition to that. Right. So one of the reasons that this is so much more complicated than what we did is these metadata things. So, I mean, we completely ignored the names of the constructors. I mean, in the case of tree, the constructors are called node and leaf, and nowhere in our representation do we keep track of the names of those constructors, which is fine for the examples we did. For equality and for serialization, we don't care about the constructor names. But if you think of something like automatically writing a show instance or read instance, especially show instance, sorry, not read. I mean, if you show, I mean, if, for example, we had our example, no, we don't have it anymore. Anyway, I could uncomment that, of course.
Or we can just load simple and restart the repo.
Yeah, sure, I can do that as well. So, I mean, we had our example tree. And I mean, if I show that, then in the string that is shown, I mean, there appears the word leaf and there appears the word node. So if I wanted to, I mean, of course, it's built in to derive show. But if I wanted to do this now by hand, I mean, somehow using generic programming to write my own version of show, then I would need access to these names. And in our version of the representation, we don't have that. So that's one reason why it's more complicated. So you can see if you squint that here in these metadata things, I mean, it's information about the name of the type, information about the, name of the constructor. So this is the leaf constructor, this is the node constructor. There's also information about the file where it's defined. So in this, on the slide, it's obviously defined in some main module. And there's other stuff about, I mean, that's something we haven't talked about yet, strictness annotations and so on. So all sorts of stuff that you can do to also if you had records, for example, then you have field names for the records. All of that is also like represented in the GHC version. Right, so that's one of the reasons why it's so complicated. So first things, I mean, we also had, I mean, the good thing is, I mean, GHG also has these three things, except that instead of U, they call it U1. And it always has this additional type parameter that we can ignore. So it has U1, which is for this case that there's no information. It has the plus and the star. I mean, the only annoying thing is it has this additional type parameter. And instead of L and R, it's L1 and R1. But apart from that, it's relatively similar to what we have. But then on top of this, every occurrence of a type as an argument is wrapped in a rec0. So if we look back here, I mean, we, for example, just had the naked A here. Here is this A, but it's wrapped with this rec0 thing. And on the other side, we had 3A, 3A. And here the 3A, 3A is wrapped into this rec0. So that's the second thing. And that is somehow as a marker to make it easier to determine where this happens, where basically I mean, you get an argument. And finally, there's this metadata stuff. So names of data types, constructors, record selectors, fixity, and all these things. And that, as I said, that's for defining generic functions. Yeah, actually for read, you also need it. Because when you read, of course, you also need to know the name of the constructors to pass it correctly. And the good news is, so the rec0 is actually a type synonym for something called K1, but it's only, this K1 is only used for the R case. So, but I mean, this also like looks complicated. And then there are these metadata things for data types, constructors, selectors, but they are all basically contained in this M1 thing. Right, so if you look back at this horrifying thing, then we see, I mean, there's the DCS, so, but that's all metadata. So metadata, 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 and then this wrapper marker rec0, and then our R, so that's this A. And here the plus as we had, and the star as we had, And here again, metadata rec0 tree, metadata rec0 tree. So if we basically ignore the rec0 and the metadata stuff, it's like what we had, plus this additional type parameter everywhere. Right, that's that. Okay. And now if we basically try our first example with the equality with right. Just a second. So how do we do this now? So if we want to do the, maybe I should delete everything and rather, okay. So let's say we want to do this now for EQ prime using, I mean, the same that we did before, but now using GHC version of generics. And maybe, sorry, maybe I shouldn't have deleted all of that. I should have, where was that? These things, these I should keep at least, these three. Maybe this and this. Just put it here. That we can compare. Right, so if you now want to do what we did here using GHC generics, it's not as bad as it first sounds. It's just a bit overwhelming with all these weird constructor names and type names. So first step is, I mean, to make it ready for, so first step is we also define something like a generic version of our class. So let's call it GEQ again. So this is now for the representation types. Right. So now we basically we give generic support to the class we are actually interested in by doing a default eq. So generic, and this is now the GHC generic. And if we have GEQ of rep, and now, I mean, these things also have, I mean, it's now type constructors. So it's, let me just see that I don't get that wrong. Right. Yeah, so we now have this stupid additional type constructor everywhere. Right, so if, so this is similar, then A2 bool, and where, I mean, this is also very similar. So we do GEQ, so eq xy is GEQ from x from y. And I need default signature extension as before. Yeah, fine, I need that. Okay, so now basically my class is ready to support generics. And so far, if we check what we did earlier, no, I delete this now. Yeah, but I mean this implementation is the same as more or less as our default eq before. The only difference is, yeah, that here now we have this additional type parameter in the generic version. Okay, and now we want to do this. I mean, for example, use it for tree. I mean, of course, we will have to write instances, but let's just check what happens if I now, sorry, if I now say e prime here. So I need to derive any class, of course, but now it complains that I don't have an instance for this DCES stuff. So that means I don't yet know how to handle metadata. But we know that all these are actually just like synonyms for this M1. So if I can write an instance for M1, then that should be fine. So let's start with that maybe. So I write an instance for, let me just check this bit. Right. Instance GEQ M1, and now it has this 3 type parameters. F where? And I need GEQF. So the idea is that I just ignore the metadata. Metadata is not important for equality. So if I have M1X and an M1Y and want to compare them, then I just compare X and Y. So that means if I have like metadata, I just ignore it and do just compare the underlying values. So that's that. And if I now go on this error message here, I see now it's why is it now? Yeah, now it's this plus. Now it's complaining it doesn't know how to handle the plus. So now we can check it our old handling of plus. Let me see whether I can basically use this one. So this case here was new because in our version we didn't have metadata, but we did have plus. So let me just to indicate that it's type constructors now call it F and G instead of A and B. So F, G. I need type operators. Okay, so now it's called L1. But this is basically the only change. So this is nice. I mean, apart from renaming it and calling it L1 instead of R1, I mean, that's good. So now if I go on the error message, it says it can't handle these constant things. Right. So let's do that next. That's also a new case that we didn't have before. Let me see for the syntax. Right. A1 TA where? So now this is a okay. Seems something is wrong there. I mean, different to the slides. Seems it now has an additional parameter or something. I don't know. Maybe
GQ prime.
no, I don't use the primes. I have a different. Just check again what the was. Well, it is 3.
The slide has the instance GQ of A constrained to GQ prime.
Right. Sorry. Yes. Thank you, Robertino. That's it. Yes. So it uses an actual EQ prime, then like this. So there it basically goes back to the original class. That's different to how we did it before. So here we just then in this case, if we have a KIX and a K1Y, we just go back to like our original class. This. Okay, and I think now what's missing? Right now the star is missing still, because in the representation we have in the node case, we have 2 arguments. But this should again be basically like we had it, just renaming a bit. So the only I can again call it F and G. And I think this, yeah, this is even the names. I mean, it also uses, GHG also uses this name for the value constructor. Okay, so now I think trees already work. Yes, so now it's fine. So now I have it for trees. One case that I don't have is this with just, I mean, the unit one, the U1. So I could, let me just, did we have an example for that where it's used? For example, maybe would use this. So if we use if I want to write instance EQ prime A, EQ prime maybe A. Now it's complaining that I don't have something for U1. Because of course the representation of maybe is, it has two constructors, nothing and just. So, and then nothing has no argument. So it's, in our notation, it would have been U plus A is maybe A. So now this doesn't work because I haven't written the instance for U1 yet. So that would correspond to this one that we had, which was actually the first one we wrote. So there, I think the only difference is that it's called U1. And now maybe should also work. Yeah, so that's fine. So we see that in principle, it's not, I mean, to write the actual stuff is not much worse than it was before. The only difference is, I mean, the names, that instead of L, I mean, that's the first difference. So instead of L and R, it's L1 and R1. Instead of U, it's U1. And we have these additional cases, basically this constant case, where we go back to our original class that we're interested in, that we didn't have in our representation. And we have this metadata stuff. But that we can always, if we are not interested in the metadata, we can always handle it like this, that we just basically drop it. So yeah, so that's that. So, and now of course I mean, we are done basically for our EQ prime. So now because I mean, now we don't have to write the generics. I mean, here we've spent a lot of time in simple to write the generics instances. GHG now takes care of that for us. And now I could do the same for my, oh yeah, and now the only question is, what do we do with primitive types? And I mean, earlier we did them in the generic version, but here we would do them in the actual class. So we would write something like instance EQ prime int, where equals built-in, for example. And we could do the same for character. We wouldn't need to do it for bool because that's generic. So we can have just instant EQ prime bool. And for lists, for example, we can have, if we have EQ prime A, then we have EQ prime list of A, that just works. And pairs, instance EQ prime A, EQ prime B, EQ prime A, comma B, and so on. So those things now just work thanks to the generic. So basically, it's not that much worse than what we did. The only, I mean, as I said, we have these two extra cases, the constant case and the metadata case, and the constructor names are a bit different, and the type signatures are more intimidating. But the actual code is basically the same. So I can demonstrate that with my serialization example. So if I go back here and copy like this, and let's adapt that to GHG generics. So okay, so slowly. So first problem, I use this deriving strategies, so I add that extension. Then I needed to import this state, monad state. Oh, I forgot to get the bit type. I mean, of course, this is bad to code duplicate, but okay, need state T. Okay, so this is fine. That had nothing to do with generics. That was just to make it pleasant to use. Okay, so this is now my, okay, now I need two class. I mean, here I did everything in one class. Now, because of these different kinds, it always needs two classes. The class you are actually interested in, and then a generic version of it, which works on these representation types. Normally, traditionally, that has a G in front. So it would be G serialize from FA to bit. Sorry, it's F. And G deserialize, maybe prime. I wouldn't really need the prime now, but just to make it clear that it's corresponding to the deserialized prime. Parser of FA. Right, and now the default implementation, that's exactly the same as before. So this is now fine. And let me just do this step by step. Somewhere there must be a big problem. The rows is not defined. Just okay, now I get errors. That's good. I hope. Hmm. 76. Now I need this G serialize here. Okay. Save. Right. Now I get my errors because I haven't implemented anything yet. So that's good. This is not good. Generalized new type deriving. State. Okay, now this is G serialize and this is G deserialize. Okay. Now I get my errors. Okay, because I haven't implemented stuff. So for example, if I start with, I don't know, with then I see I don't have the plus, for example. So let's just, I mean, that was the most interesting case. So let's just copy what we did there before and try to fix that. So now it's G serialize F, G serialize G, G serialize F plus G, 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 G. It's called L1, R1, and it's G, G. Okay, and here G, G, and L1, R1. Okay, need some more imports. Okay, this looks good already. And okay, bool still doesn't work because that's the metadata thing now. So let's write the case for the metadata. And let me just steal that from here, because if you're not interested in metadata, as we, for example, for serialization, we are not, then you can just always handle it like this. So let me do this here. Of course, now it's G here, here, and serialize, and only one argument. Nice X. And GD serialize is okay. Now we need, I mean, we have a serializer for the rep one for X. So GD serialize. And now we want to do the same trick again to get to M1. Oh no, I think it's just M1. Right. Okay. So that's the constant case. And now I've got not the constant, the metadata. So now I got rid of the metadata. So now I need an instance for U1, because bool, of course, is U1 plus U1. So I need the instance for U1 that we had here. So that's again the one we already had. So let's put it here. So G serialize U1, where I just don't waste any bits on it. One thing now, bool should work. Yes, bool is now fine. Now this the star, of course, is missing, and the represent this constant type. I think the problem is both. I mean, here, for example, yeah, whatever. Let's start with lists. So here we see the star. So, but that is again just renaming of what we did before. Let's put it, I don't know, here, that we have the same order as before. So G, F. Of course, I wouldn't have to rename this A to F and B to G. I just do that to make clear that it's no longer a type, it's now a type constructor. And we tend in Haskell to use letters like F and G for type constructors, like functors and so on. Of course, semantically, it doesn't make a difference. G there. G, 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 G. Okay. Looking good. So now I think only this constant case is missing. So there we can again steal it from here, because I always forget the type parameters. Let's put that here. Okay, so this is now serialize A, not G. So this is the case where we basically tie the knot and go back to the original class. So in order to G serialize a K1, I serialize the X. And to get a parser for K1, I just use a parser for the X and then fmap K1 over it. No, that's wrong. Maybe the wrong direction. No, hang on. Sorry, this is the underlying, so without the G. That's the point. There's no G here in this case. Same as for equality. When we wrote this case here, it was also the other class. And we defined it, in this case, the generic one by reducing it to the original class. Okay, so now I think everything, okay, this is not defined. So this is now called eq prime. And why is this not? Okay, because we didn't define derive generic. Okay, and now this all works again as before. So as I said, so ours is of course simpler, but it's not that bad with GHG, especially if you're not interested in the metadata. So if you're not interested in the metadata, the case that handles the metadata can always be like this, where you basically just remove this M1 and we need this constant case. And the other cases, the other three cases are more or less exactly like we did. I mean, it looks a bit more complicated because we have this additional type parameter, but the actual code we write is the same as before. And of course, if you use the GHC approach, we don't have to write the generic instances ourselves. So then we don't even have that. So we just use our types and that's that. And now I think that was more or less the lecture. Yeah, here's one slide about, but I think we can skip that. I mean, one of the reasons why they use these complicated, this kind star to star, is because you can also do generics for things like functor, traversable, foldable, and so on. So not just for things of for type classes that take something of kind star, but also something like functor that takes something of kind star to star. And then it's another class. It's called generic one for things like that. But we see the representation type is also star to star, same as the one for generic without the one. And then there's a from one and the to one. And then there are some additional type constructors. And you can also derive that. I've never used that, so it's just for your information that one can do that. And I mean, it's also not very common that you actually have to do this. It's much, much more common that you do this. I mean, you use it. I mean, it's very common that you, for example, use ASON or binary and need JSON representation for your types or serialization, binary serialization for your types. And then you just derive generic and the type you're interested in, the type class you're interested in. So that is very common. Like that's like every Haskell developer does that like 10 times a day. But that you actually implement it, I mean, author a new class and then add generic support for it. I think I've maybe done that once. I mean, for fun, maybe like now for lecturing, but for real, for production, I think I've never done it. So, I mean, you don't have to worry, but it's nevertheless, I think a good idea to know at least the idea behind it. So the idea is to basically map more or less all types to this handful of generic representation types that just use these three constructs, the U, the plus, the times, or the star. Then you only have to implement your type class instances or write your generic functions for those types. It's not just for type class instances. I mean, you could write generic functions for all sorts of things. And then use the to and from to basically marshal between your type and the generic representation. So that's the idea how generics works. And if you have like this automatic deriving of generics, so you don't have to worry about like writing the representation type by hand and writing the from and to by hand, that all happens automatically by the compiler. So then all you have to worry about is actually implement the thing you are interested in, the generic function you're interested in, like in my case, the G serialize and the G deserialize prime for those handful of constructors or types. And once you have done that, you basically get it for infinitely many types that implement generic or instances of generic. Right, are there any, I think that was it. So it's powerful and there are other ways to do it, something very similar. Generic, I mean, this GHC generics that I showed now just has, I mean, the built-in support by GHC. But the others, you don't normally also don't have to like do anything by hand. because they then have ways to whatever do their version of generics automatically, and then so yeah, it's all similar. It all has its own advantages and disadvantages. And in the next lecture, so I'm not sure what we should do now in the last half hour, whether we should start with the next lecture or whether we should do some other example. But anyway, the next lecture will be about template Haskell. So that's full meta programming extension to Haskell. So I don't know who of you knows maybe C++ or Lisp. So Lisp is famous for its macro system. So I mean, a macro is basically a program that writes programs. So you, and if that's part of your compiler stages, then you can. I mean, Lisp it's very important, but C++ has templates, and various other programming languages have macros. So I mean, the idea is that basically at compile time, I mean, you have code that writes code producing code, and then that can be part of your final program. So these macros expand and get evaluated at compile time, and there are various reasons why you would want to do that. For example, performance. Or also what we talked about today. So all these things like automatic instances for type classes, you can also do with template Haskell. So template Haskell, I would say the learning curve is maybe steeper, but you also can do more. You can do almost everything. And right, so it's and it's all type checked. So I mean, one of the problems with Lisp macros is that I mean, Lisp is untyped anyway, so it's very difficult to actually get that right. But in Haskell, I mean, the compiler helps you and tells you when you made a mistake. And you can basically really manipulate the full Haskell syntax tree. So you can see the whole program or function or type, everything about it, and like manipulate it and create your own syntax trees. And it's right. So you have to do more work to derive classes using template Haskell, and it's trickier to get right. And you have to worry about names and name clashes and so on. But and right, template Haskell, I mean, as we saw this data type generic functions, I mean, it's just normal Haskell functions. So they are type checked basically I mean, while you write them. But template Haskell only checks the generated code. So you can basically write code where the generated, I mean, template Haskell code where the generated code is not type correct. And then the compiler will catch that, but only when you actually try to compile your program, not when you write your macro, sort of. But it's definitely an interesting and powerful technique. So I don't know, yeah, what
The
here?
type template Haskell is also checked after splicing, or I thought it was the actual meta program that
No, I think maybe this slide was, I'm not sure.
because
Actually, that's the point. I mean, template Haskell actually checks during already. I mean, when you write the splice, so that's better in that regard. But there are only certain things you can do with type template Haskell. So, like, I mean, you can only do expressions, whereas with template Haskell, you can also do declarations and patterns and so on. So, but yes, where you can use type template Haskell, I think that last remark doesn't apply, if I understand it correctly.
right. Yeah.
And I mean, and that is also used a lot in the wild, maybe not as much as generics, but also, for example, I mentioned that a couple of times for optics, and for example, to get optics, I mean, you can use template Haskell or the major optics libraries like Lens. Provides a template Haskell function called make lenses, and then you just write make lenses for my type. It's one line, and then you get all the lenses for your type automatically. So we can definitely look at that. And there's also something cool called quasi quotes, where you can, in principle, I mean, it's almost as if you can extend the syntax of Haskell. So you can pass arbitrary strings and convert them into Haskell types at compile time. Which is also very cool. So we can look at an example, for example, to generate HTML or things like that with Haskell quasi-code. So that's also template Haskell. Yeah, I don't know what. Do you have any suggestions? Should I do another example generics or show something with template Haskell or?
I mean, we have the template Haskell lesson, and on top of
Yes.
that, the web lesson, we use Blaze HTML with template Haskell.
Mm-hmm.
So maybe we will have plenty of examples of template Haskell.
Right. Good. Is there something that I could still? I mean, I could write a C instance for int. I'm just not sure. That has little to do with generic programming. It's more parsing.
Maybe if anyone has any questions, we can answer a couple of questions.
Sure.
Also, another thing that you said that sometimes when using ASON, you want like a specific representation. You have the option always to like do it by hand.
Yes.
Yes.
You do, and I think I mean, you can definitely do it by hand, just really, I mean, explicitly do it by hand. But I think there's also a way to like still derive it basically, but give some options on top. I mean, I think that I've never done that, I think, but there's a way to sort of automatically derive it, but with options. And then you can say use camel case for the field names or Pascal case or whatever. So I think that you have, I mean, if somebody's interested in that, we can try to understand that quickly if that's possible.
And we also have one question.
Yes. What's
Can
that?
we do generic programming for programs as data? So I think he means like to generate data or
yeah, or generate programs. I think that's the.
If you can add.
Sorry.
Like free monads, says Jason.
Oh. I mean, in principle, sure, we could do something. I mean, I suppose we could, for example, actually, that's a good, yeah, but that's again template Haskell. But that's a good remark because I mean, we had this thing that once you have your functor, then you have to, I mean, the operations in your functor, you have to basically then get them in your free monad, and that's also boilerplate. And that's again something that in the free package, there's a template Haskell function to do that automatically, where you don't have to do that by hand. Maybe, I mean, an example would be good that it's not just about type classes. I mean, it's not necessarily about type classes. You can do other things. Just try to think of an example.
I think Andres used this power. No, that's for template.
That's
Haskell.
also template Haskell, yes. Yeah, maybe it's not a good. I think normally it is type classes with generics. I mean, if I could think of something, there's some other interesting class one can quickly implement. Or, I mean, of course, one could try to do something with the metadata, but what do we have? We have ort, eq. I mean, that's boring because they are already supported. Serialization. Yeah, one thing maybe default. There is, and maybe that's not a bad example. I mean, there's actually a class called default, I think. on Hackage. Default package data.default. So the idea is that often you have types where you have a default value. So it's a class for types with a default value. I'm a bit surprised that there is no method. I mean, there should be, it's called def, but I don't see it here. So it's a bit strange. But anyway, so we can, I mean, that is actually maybe not a bad example. So yeah, let's just do another example. So the idea is we have a class, it's called default. So that exists on Hackage, but it's not part of the standard libraries. Where you have one method def, and it just gives you a value of type A. The default value. So sometimes there is like one like special element in a class, in a type. And
Like the state of the emergency, like no emergency, warning, error.
yeah, I'm not sure whether this is a good, maybe that is a, maybe it's at least it's not a bad example. Right. I mean, for example, you could have an instance default int where def is 0, for example. Or you could even have that for num a default. No, I think this won't, that will complain about instance head no larger than the, yeah. Maybe not a very good example, but anyway, we could try to do generic support for that. So, I mean, the steps would be, so we define this generic version, class G default, F, where G def FA, so always this additional type parameter. And now we could write some instances. But of course, the problem is, I mean, not all types support that. Or, I mean, for example, bool. I mean, what's the default element of bool? Is it true or false? I mean, it's not clear. So if we have this plus, do we choose? But I mean, we could do that if we want. So let's see. We could do. So for example, we could always prefer left over right. So let's just copy these cases quickly. Sorry. So that we have to do to cover everything. And I mean, you also don't have to implement everything, actually. That's maybe was a good example. So yeah, time should still be enough. So, okay, first is this constant thing, and there we can just say, okay, if A has a default, then we have G default for this. I mean, now it's simpler because we only have this G def. And there we can just use K1 def. So we take the X default and apply the K1 to it. So that's easy. Metadata, we can also, that's also easy. Again, gdef is just, so the default value of this is just def. Why is this now complaining? Oh, okay. Actually, sorry. Yeah, of course. Default. So the default constant is just, I just take K1 of the default the M case, bit surprised that that it doesn't complain there. Just a second. I thought I needed the M1. Yes, indeed. GDEF, sorry. Okay, right, so now the U, I mean, there it's clear. So G default, I mean, we only have one value, so the only possible default value is that one. And the star is also clear what we do. So if we have G default F and G default G, and we have G default F star G. So G default is just, I mean, we must of course take the defaults. Sorry. On both sides of the product, GDEF. Right. This is not so clear. I mean, if we have a left and a right, is it like is the default the left or the right? But one point of this example is that you don't necessarily need that. I mean, you don't have to implement everything. That just means you can't derive it for any generic class, but only for some of them. So now that we have this, I mean, we have default for int, which is 0, or we don't, because I'm in the, because I didn't save. What's the problem now? Why? Okay. Okay. So for int we have, but I mean, that's no surprise because we defined it. But now because we also have it for star, for example, I mean, because we have it for U1, we, for example, also have it for unit. I mean, we should have it for unit. Maybe I must, okay, fine. I must instance default unit. Okay, fine. Yeah, sorry. Of course, I must have the machinery here. So I must define default. So if I have generic A and I have G default of rep A, then I have a default A, namely what? Well, I take the G default, which is in rep A, and then I do 2 to go back to A. So, okay, so now I have, for example, for unit, and I have instance default A, default B, default A comma B automatically because I have the star case. So now I have default, for example, of int comma int, but int comma int comma int probably not, right? Because I mean, I could of course write that. And that's often what you see, what people do. See, anyway. Right, but I don't, for example, have it for, I mean, for plus. I mean, and if I try to do something like instance default A, default list A, then it complains and will tell me that I didn't write an instance here for plus. I mean, of course, I could write one, but it's not clear whether, I mean, if we wanted to, we could. So I could say default F, default G, default F plus G, It should be here. And then what should gdef be? Well, now we have to decide. For example, L1 gdef. And then I wouldn't even need an instance actually for the right, because I always use it for one. But I mean, whether I want to do that is of course a different story. But now I also have it for lists. So now I have, and that's of course now the empty list. So for a list of strings, interesting. Okay, that's interesting because I thought it would now have picked the, did I reload? Somehow. That's a bit surprising because I would have thought that the empty list is the left and it would always pick the empty list then. But obviously it doesn't. So maybe let me just ask for the representation of list kind prime list, for example, string rep, of course. So it's indeed it's interesting. No, it's not interesting. Oh, it does use the U1 first. I'm a bit confused. Why does it ask for? Do you understand that, Robertino?
No, maybe it tries to evaluate everything because no, I'm not sure what the decided lazy does, the type level.
Mm. But I mean, I only. Oh, right. I do. Yeah, no, because I'm stupid. I mean, I wrote this here that it needs default A, but it doesn't. I mean, now I could just do this. So it was my own fault. Now it works.
Okay.
I added a constraint that was not necessary. I mean, now it's not necessary. Now I also have like instance default maybe A without any constraint on A because it will just always pick nothing. Def maybe whatever double. Right. But as I said, I'm not sure that's a good idea to do this, that you always prefer the left. But nevertheless, it's a way to basically in almost every type automatically get a value. I mean, we can, for example, now we had our two examples here. So I can now also implement do default. And for our tree type, I can do default. Of course, for all sorts of other types, I could do that as well. Where's our tree type? There it is. Serialization I could also put here and default. And now I mean it will be boring, I suppose. Okay, so now I mean obviously I need a default A, but if I for example do default tree int, it gives me a leaf with 0. I mean default tree character it wouldn't because there is no default character. Yeah, but and rows trees should also work. Did I add it already to rows trees? Yes, I did. So for example, and there also we need the default A, but for example, default of a rows int is fork 0 and empty list. Yeah, that's also, I mean, one thing is, I mean, it's quite nice if you can automatically generate elements of types. So maybe default is maybe not a good word, but at least you have like one value of a type now, of a lot of types. And that is actually would be a good example. Basically, to get automatically all values of a type or some. I mean, if it's finite types, so maybe I mean only 4 minutes, but maybe I can pull it off. So this is actually a better example, I think. So instead of, let's call it class enumerate. So that's a class for types where I can list all values of that type. And in this case, I must map 2 over y. Okay. Let's not do this. And now I have G enumerate F, where G enumerate the list of FAs. Right. So for this, so if I have enumerate here, it's this, and G enumerate is just K1 mapping K1 over enumerate. G enumerate F, this is the metadata stuff. So G enumerate is just mapping M1 over G enumerate. Okay, this is now interesting because if I enumerate the type with one element, it's this one element. Let's enumerate. Okay, what do I do here? That's interesting. So how do I enumerate product? If I can enumerate both factors. So I can, for example, enumerate the first factor, enumerate the second factor, and then do that. X star y. Y is G. Why is this complete? Because default, yeah. Okay, and the last part is also interesting because there I can concatenate lists. So almost done. So G enumerate. If I have left and rights, then I can map L1 over enumerate. So now I get all the lefts, and then I can concatenate it with mapping R1 over all the rights. And why doesn't it work? Because that was the earlier example where I didn't need the G. G. Right, of course, that will only work for finite types, obviously. But if I have a finite type, so now I can, for example, instance enumerate bool and instance enumerate A, enumerate B, enumerate A comma B. Why is this complaining? Somewhere is the default still. Here probably.
Yes, and 170.
Yeah. Okay. And I can do the same with either. Enumerate, of course. Right, and now can, I mean, of course, it won't work for stuff like lists or trees because there are infinitely many. But for example, I can enumerate whatever, either pair of booleans or a single boolean or unit. something like this. Why? Okay, list, fine. List of these. And probably for unit, it's not right. I would need the unit instance. Then we are done. Right. And now it lists all possible values of this finite data type. And of course, I could try it for lists, but then it will just not stop, but lists I don't have. I mean, I shouldn't do this, but if I do this, I mean, I can derive the instance, but just fine. If I do this, then it tries to write down all lists. Cool. And okay, fine. It never uses a fault, so true. So it starts with empty list and the one with one fault, with two faults, with three falses, and so on. Yeah. So I mean, one could try to write a more, more clever instance that somehow, whatever. But this one shouldn't use it. But anyway, that's also cool. I mean, this may be better than this default. So for example, you could use something like this for exhaustive testing. There's something like small. I mean, we looked at quick check where the idea is to randomly generate test cases, which is very cool. But there's also something called small check. I never used it, no idea how it works. But I would imagine it works something like this, so that they exhaustively test like all possible values. But of course, most data types are infinite, so they stop somewhere. But basically, the idea that you systematically try every possible value, and this is would somehow go into this direction. So I mean, now we saw lots of examples how you can actually do this relatively quickly in 5 minutes for a given type class. Add support for generic deriving. Are there any last questions before we stop?
Not so far.
Okay, then I suppose right. I said next week, so we don't have classes Monday and Thursday because of our education meetup, and then the other Monday I'll continue with template Haskell.
Okay.
Okay, then thank you very much, and use the week next week to like get your exercises done and homework and so on, and go over the material again. And then the week after, as I said, template Haskell, and then on the Thursday, actually, Robertino will give a lecture on web programming, and I think then we're done with Haskell for the time being, right?
Yep.
So after that, then, so next week you study by yourself. Week after, 2 more Haskell lectures, and then we start with smart contracts. First with Marlow and then with Plutus. Okay, so lots of stuff to look forward to.
Yeah.
Okay, then talk to you in a bit more than a week.
See you, everyone.
Okay.
See you, everyone.
Bye.
Thank you. Bye.